In our earlier lectures, what we saw was that entropy as a function of UVN or U, internal energy as a function of SVN, are the fundamental relations of type 1. Relations of type 1, and we also saw that for an isolated system which is not allowed to exchange energy with the environment, the maximization of the entropy is equivalent to the minimization of the energy, and that takes the system to an equilibrium state. At the equilibrium state, the entropy is maximum. Further, we also studied that both S and U are extensive quantities, which implies that they are additive. And the consequence of this extensivity is that they are homogeneous of degree 1. And since they are homogeneous of degree 1, they must satisfy the Euler relation, and the consequence of the Euler relation, this homogeneity property of the internal energy and the entropy, leads to the Gibbs-Duhem relation. So today what we are going to do is we are going to slowly, very quickly and briefly review partial derivatives, and then we are going to move on to something else. Now, partial derivatives particularly is the area of a multivariate calculus. So if I have a function of x and y, earlier for one variable calculus, I know that if I have a function of afx, then df I can write down as df dx. But now I have a function of two variables, and therefore I want to find out the total change in the function df. This essentially means that I have to go a distance dx along the y direction and a distance dy along the y direction. So I go a distance dx along the x direction, a distance dy along the y direction, and I want to calculate the change. That, in a very simplified notation is del f del x, del f del y, dy, right? Now suppose that there is a functional relation between three variables x, y, z, so that we can write down f of x, y, and z is equal to 0. This is, if you can imagine the example being s of uvn or u of svn. So this describes a manifold as is given over here. Then if such is the relation, then I can write down dx. X can be a function of y and z as del y del x dx plus del y del z dz. I can do the same exercise and write down dy as, this relation is wrong. So then I can write down, if x is a function of y and z, then dx is del x del y dy plus del x del z dz. Here y is held constant, here z is held constant, and I can do the similar exercise in writing for dy, where I will have del y del x dx plus del y del z dz. Here x is held constant and here z is held constant. So if I now substitute dy over here, then this becomes del x del y z constant times del y del x z constant dx plus del y del z x constant dx plus del x del z y constant dz. So dx is equal to we had del x del y dy z constant plus del x del z y constant dz, and dy was del y del x dx z constant plus del y del z x constant dz, and we substituted for del x, we substitute dy over here. That essentially means I have del y del x z constant dx plus del y del z x constant dz plus del x del z y constant dz. Open the brackets. Del x del y z constant del y del x z constant dx plus del x del y z constant del y del z x constant plus del x del z y constant times d of z. Now imagine you hold x is equal to constant. This implies that dx is equal to 0, in which case the coefficient of dz must vanish, because this equation then just becomes this is equal to 0, and if it is valid for all values of z, then it must be that the coefficient must vanish. Therefore, you have dx dy del x del y z constant del y del z x constant plus del x del z y constant is equal to 0, which means you come up with a very nice identity del y del z x constant and del z del x y constant is equal to -1. This is what is called a cyclic identity. Now you hold z is equal to constant. So you fix the z, and this implies that dz equal to 0, and therefore you see the left hand side and the right hand side, which is this and this, is an identity. So this means that del x del y z constant del y del x z constant must be equal to 1, which gives you the reciprocal relation that del x del y z constant is equal to 1 over del y del x z constant, right? So you must pay attention to the quantities which are being held fixed in the partial derivatives, right? If I now want to apply this to our hydrostatic system, we will take this relation, the cyclic relation, and we will consider P, V and T. If I apply this to PVT, then it means that del P del V temperature constant Then I have del V del T pressure constant, and I have del T del P volume constant must be equal to -1. So this implies that del P del V temperature constant, del V del T pressure constant is del P del T volume constant with a minus sign in front of it. But the compressibility, which is the isothermal compressibility of the solvent, is defined as -1 by V del P temperature constant, right? So this term is a response function and is called the isothermal compressibility. The other one, which we'll call beta T or just beta, is 1 by V del T pressure constant, and this you know is the expansion coefficient. In the former case, the isothermal compressibility or the compressibility in general determines how your system is going to react if you apply an additional pressure, compress or remove the increase or decrease the pressure. In the second case, it determines how the system is going to react if you supply heat to the system, which means if you increase the temperature of the system. So once I know, so these are my this is my response function, and the advantage of this response function are that these are experimentally measurable. So I can know their dependence on pressure, temperature, and all these things. So if I have this, then I quickly look at the equation that we had written down over here, and then I have del P del T volume constant is beta over kappa T. We will use this later on on several occasions, but the simplest application is if I want to, for any hydrostatic system which is a fluid, if I want to write down P as a function of T and V, then this implies that dP is del P del T volume constant dt plus del P del V temperature constant dV. And this one I have already calculated just now. The first term is the one which I have calculated just now, which is this. So therefore it follows that this is beta over kappa T dt minus 1 over kappa V dV. So you see, now you have a very nice equation. You don't even have to know the equation of state. If you can measure these quantities experimentally, if you can measure kappa T and beta experimentally, you can find out how the system is going to behave, right? So if you say that, well, I change both T and V, then I know what is going to happen to this system, correct? Finally, we come to what is called an exact and inexact differential. This we have already done, and the consequence is that the example is first that the entropy and the energy are exact differentials. Why are they exact differentials? Because they do not depend on path. And once they do not depend on path, therefore I can write down the following way. But before we do that, what we want to say, so what exactly do we mean by exact and inexact differential? As we had shown before, that if f is a function of x and y, then df is equal to del f del x, y constant dx, plus del f del y, x constant dy. But the function f is analytic, Therefore, if you take the second derivative of this function, which means del xf, which is equivalent to, you are taking a derivative del y of del f del x, and here you are taking a derivative which is del x of del f del y, they must be equal, right? So therefore, I have del y of del f del x must be equal to del x of del f del y, and this is the condition for f to be an exact differential. So if you can write down the function in this particular form, given this f, if you can write down df in this particular form, then you know that it's an exact differential, which means that for any quantity, now I have changed it, the notation, plus b xy dy. What does this mean? This means that I have replaced del f del x is equal to axy and del f del y as bxy, but with the understanding that this can be any, this may not be del f del x, this may not be del f del y, so this can be any functional form. So if I am given any arbitrary differential of this particular form, if it was an exact differential, then I would have this equality. For an exact differential, I would have this equality satisfying, but in principle I can have any function times dx, any function times dy, and if I want to find out whether this function f is an exact differential, I will simply do del a del y must be equal to del b del x, and if this is satisfied, then I know that the function, this is an exact differential, which means it is path independent, right? So now you know how to determine exact and inexact differentials. So this we shall use, this is the criteria of an exact differential, we shall use later to find out, determine what are called Maxwell's relations, but not right now. So right now it suffices to say that if this relation is valid for a differential, then then the function that you are considering is an exact differential, or the differential is an exact differential, and the function is a state function in the sense that it does not depend on the path that you have taken. What we want to do right now is move to something else. Now, whatever we have been discussing so far, as we summarized in the first part of the lecture, S and U as a function of SVN, these are my fundamental relations of type 1, and these are valid for an isolated system. But isolated systems are very, very difficult to find. In reality, whenever you do an experiment, there is something what is called a path which comes into the picture. And the bath, essentially, it has several way of people calling it. It's a reservoir, it's an environment, whatever it is, but they play a very significant role. For example, if you're doing it in an experiment, you're doing an experiment in a beaker with a liquid, then you know that this part of the surface is exposed to the atmosphere, right? So, and it maintains a constant pressure. If you are doing it with a closed beaker, but fixing the temperature, which means that you have applied a thermostat to the system, which is either you have put it on a heater or which is connected to a thermostat that maintains the temperature of a system. So here temperature is constant. So all of these in an experiment, realizable situations, these become very, very important. So the question is then, you would like to deal not directly with the coordinates that you have over here, but essentially you want to bring in these forces because they are being held fixed, and therefore the differentials are also going to be easy to manipulate. So the question is how to do that. Now to answer this, we shall look in some different area. So let's consider now y as a function of x, right? Now typically what happens is, if I want to plot this function, if I know the functional form, for example, I can take yx is equal to a times x square, and all of you know how the plot is going to look. Let's make the plot like this. So this is y is equal to ax square. But now, if you know the function, you can definitely plot it. You can find out the derivatives to calculate the extrema of the function and the asymptotic behaviors as well as the behavior near zero to plot the function. Or you can use a plotting software, that is even more easier nowadays. But now, alternatively, you see, what I can do here is I can specify the tangents. Let's say I specify the tangents. So this is my tangent at this point. This is a tangent at this point. This is a tangent at this point. The question is, can I reconstruct the function from this tangent? Clearly, if there are only 3 tangents, then you can say, no, how can I do that? For example, I can have a curve which goes like this, and then like this. This is a different curve, but you see the tangents are the same. Therefore, if I just give you only a finite set of tangents, if there is only finite set of tangents, then you may not do it. Then you cannot extract the same information, or you do not encode the same information. But in principle, since if I can specify the tangents at 3 points, of course I can specify the tangents at all points. So that would mean that I have specified the tangent here, 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 all along the curve, and then you see no longer there is any ambiguity. Then the curve has to, I can reconstruct the curve from the tangent itself. But the tangent, equation of a tangent is mx plus c, right? And that is a very, very simple equation. It's an equation of a straight line. So now, if I specify the tangents only at these 3 places, then of course you can see that it's not possible to reconstruct back the function, because the red and the black curve have identical tangents at these points. But if I can specify it at 3 points, I can specify it continuously at all points on the curve. And then you see there is no ambiguity in this. I can reconstruct back the whole function. So the idea is very nice. And I know that here the equation is very, very simple. The equation of a tangent is y is mx plus c, where m is the slope and is dy dx at the point x equal to x naught, and c is the intercept. So therefore, I have to define a function c of m, which is y minus m times x. The moment I define this c as a function of m, if m varies along the curve, so does the intercept. Therefore, I have encoded all the information that is required to reconstruct back the curve. Let's see. So y is equal to ax squared, that is the function that we started off with, and then it follows that dy dx is twice ax, which means m, which implies that m is equal to twice ax and x is equal to m by twice a, correct? Y is a m by twice a whole square, which is m square over 4a square, and therefore c of m is m square over 4a square minus m square over twice a. Sorry, this has to cancel out, this has to be a. So this is minus m square over twice a. And this is the function that I am looking for. C of m is minus m square over twice a. But then you can ask me, given this C of m, how do I construct back the function? That's a valid question. So let's start off. So I know dy dx is equal to m, therefore dy is m times dx. Now c is equal to y minus mx, so that dc is dy minus m dx minus dx dm. But dy is m times dx. This is what we have got from the definition of the slope, and therefore it follows dc is minus x dm, or x is minus dc dm. This is the answer that we are looking for. Just as we had dy dx is equal to m when we went from the xy to cm. This is the answer that we need if we want to reconstruct back the function. So if c of m is minus m square over twice a, then dc dm is m over twice a, and minus dc dm is m over twice a. Am I right? No. So it's twice m over twice a, which is m over a. Let's just rub this out. Right? Which implies that this is equal, so m over a is equal to x, or m is ax. So there is a problem somewhere. Yeah, the problem is over here. You see, this is m square by 4a, this is minus m square by 4a. And if this is minus m square by 4a, then this has to be 2. This is the error that we did. So if this is 2, then this is twice ax, right? So now we have m. So c of m is minus m square over 4a. M is twice ax. Now y is mx plus c. If y is mx plus c, then you see that this is twice ax square. If you substitute for m over here, plus c is minus m square by 4a. So let's do it carefully now, so that we don't make any mistakes. This is minus 4a square x square divided by 4a, which is twice ax square minus ax square, and the answer is y is equal to ax square. So you see, whatever you have encoded over here, that completely contains the information about this function y equal to ax square. So though both the descriptions are equivalent and equally valid. You could have argued that, look, I have specified c as a function of m. Why not specify c as a function of x? See, this will not encode the same function, because if you see, y is equal to ax square and y is equal to a x minus let's say alpha whole square, where alpha is a positive, well, alpha is a shift essentially. So essentially y is equal to ax square is this, and y is equal to, this is your alpha, will have the same value of c of x. So then the information contained is not the same, and from this definition, that if you just have c as a function of x, you cannot reconstruct back the function completely. So the bottom line is that I can equally define this c of m as y minus mx, and this procedure is what is called a Legendre transformation. You probably have done Legendre transformation in a different way, but this is what the Legendre transformation means. What does it mean? look at it very carefully. You were given a function y of x. You have taken that function as your input and you have replaced x to get a new function which is now a function of m. So this is the prescription if you want to replace a variable. In classical mechanics, the Lagrangian is a function of p, q and t, right? Or in some, so p doesn't enter over here, you write it down as q, q dot and t. Then the momentum, the momentum is del L del Q, and you can eliminate Q dot by writing down in terms of this momentum, and this is what is called the Hamiltonian of the system.